This is measures of dispersion. How spread out is your data? Talked about when we were dealing with the mean that sometimes the mean doesn't really represent the data very well. Well, our first one we're going to look at is the range. This is the difference between the largest value and the smallest value. Range is equal to largest value minus your smallest value. So, very simple formula. Let's take a look at an example of that. We have 33, 45, 5, 31, 50, and 85. Now range, remember, is our largest value minus our smallest value. Well, if my largest value is 85, which is in this example here, our smallest value is 5. So the range would be 80. Now this may not really represent the data that well. It just shows how spread out is it. It doesn't say how many are in the near the 20s, how many are near the 30s, or how many are near the 85s, for example. Just from the smallest to the largest. Now we got something called a standard deviation. This is a measure of variation of values about the mean. And we'll come back to these formulas in more detail, but we have a population standard deviation. This little O looking thing at the flip, that's lowercase sigma. And it says it's square root, and then remember this is uppercase sigma. That means we add together. So our x values minus the mean squared, and then add them together. Divided by capital M. Capital N is how many are in our total population. And mu is our population mean. Okay. Now our sample standard deviation. And that's S is equal to square root. And then I'm going to take the x values, subtract the sample mean, and square it, and then add them together, and then divide by n minus 1. Little n is how many is in my sample. We've got a shortcut formula, which we'll show that one, so we'll come back to that. Let's do this by hand. Okay, so we got 5, 10, 23, and 2. And standard deviation is something you should be able to do by hand, even though technology does it fantastic. I've had many students come back and tell me that other professors, other instructors in other classes will require them to show the steps by hand. Now I'm specifically going to find a sample standard deviation. The population standard deviation is the same formula, except for instead of dividing by n minus 1, you divide by n. So let's look at this one. First thing, our x values. The x sub I you see right here, the I represents you could have 1, 2, 3, 4, however many data points. So we're going to have 5, we'll have 10, we'll have 23, and we'll have 2. Okay. Now we need x bar, so I'm going to add these together, and just so I don't have any screw ups in my example here, I'm going to do this 5 plus 10 plus 23 plus 2. That gives us 40. Okay, I need to scroll down a little bit more space. Okay, so our x bar, we're going to take our 40, and we got 4 data values, so we'll divide by 4. So that gives us 10. That's our sample mean. Now from a formula here, it says x sub I minus x bar. So we need a column for x sub I minus x bar. So we're going to take this each of these x values, and we'll subtract the x bar. So 5 minus 10 will give us negative 5. And we got 10 minus 10, which gives us 0. 23 minus 10, which is 13, and 2 minus 10, which gives us negative 8. Now let me double check myself here. 5 minus 10, 10 minus 10, 23, 2, okay. 5, 0, 13, negative 8. That's what's inside of parentheses. Well, then we got squared, so we need another column. We're going to square those. So we're going to have negative 5 squared, which gives us 25. We're going to have 0 squared, which gives us 0. We'll have 13 squared, which is, I think, 169, but let me check. 169, yeah. And we're going to have negative 8 squared, which is 64. So that's this right here. X minus, or x sub I minus x bar squared. Now we got this E looking thing in front of here. That's our uppercase sigma. That says now add those values together. So I want to add these values together. And I'm going to use technology here and not do it by hand. 25 plus 169 plus 64. And we get 258. Well, now we're ready to plug it into our formula. So S is equal to square root of the sum of xi minus x bar squared divided by n minus 1. Well, we just said the top part is 258. Now n is how many data points we have. Well, we have 4. So we have 4 minus 1. So we got 258 divided by 3. That actually goes into it evenly. What's that give us? 258 divided by 3. 86. And then square root of 86. If I plug that in my calculator, I get 9.3. Would be my sample mean. Now I put S there to represent sample mean. Now there's a shortcut formula to do that. Actually, let me mention population standard deviation first. Again, exactly the same formula, but instead of dividing by n minus 1, we just divide by n. So the difference on it is we divide by 4. I'm not going to actually create that, but you have to specifically look at what they're asking for. Are they asking for sample standard deviation or population standard deviation? There's a shortcut formula. So let's look at this in detail. Looks more complicated. I always show that to students. Well, that's more complicated. It looks more complicated, but it's missing an important piece. If I come up here, oops, right there, look at our sample standard deviation. This has got x bar. This doesn't have x bar. And you're saying, well, what's the big deal? It didn't look that bad. Well, I designed this to come out really nice. Imagine if you have a bunch of decimal places here. This was 10.137457913. Now you don't want to round it because you start rounding early on in your problem and you get errors. Well, when you put a bunch of decimals in here, this becomes nasty. The benefit of this formula is it doesn't revolve around the mean at all, so that there's less decimals. I shouldn't say there's none, because there is still some. Well, let's look at this problem reworked using the shortcut formula. So let me write down the problems down again. So we got 5, 10, 23, and 2. And we use our shortcut formula. Well, to begin with, I see over here we got sigma x, so I want to add together the x values. So let me first put the x values down. 5, 10, 23, and 2. And adding together the x values, and you can drop the sub I. What is that, 40? Now that would handle this piece right here. Now n's, I know that's how many we have. Now this is a neat x squared. So I'm going to square each one of my x values. So I got 5 squared, I got 10 squared, and 23 squared, and 2 squared. 5 squared is 25, 100 squared is 100, have no clue about 23. Let me see. 23 squared is 529. And 2 squared is 4. Well, this sigma that's in front of it means I now want to add those together. So I'm going to sum these. And let me see, 25 plus 100 plus 529 plus 4. And we get 658. So now I have this, I'm ready to plug in my formula, actually. So we got n sigma of x squared minus sigma x, all that squared, divided by n times n minus 1. Okay, now n would be 4, that's how many we have, times sigma x squared, that'd be 658, minus sigma x, 40, all that squared, over 4 times 4 minus 1. Okay, so let's see. 4 times 658 minus 40 squared, 1032. And 4 times 3 down below gives us 12. And square root of 1032 divided by 12. Get 9.3. And that's our sample standard deviation, which matches what we have here. But again, we didn't have the possibility of the x bar giving us some nasty decimals. Well, let's use technology to do this now. So let's go to our calculator and clear that out, exit out of here. I'll do second mode, exit out. Now I'm going to go into my stat, go into my edit. Now I want to put my numbers in. So I'll press delete over and over to clear those out. Quite a few numbers. Okay, so then we'll put in 5 inner, 10 inner, 23 inner, and 2 inner. Now this is our steps from the last section, one of our stats. So do second mode to exit out. I'll go into my stat, right arrow to calc. One of our stats is selected, so we'll press enter on it. Now this assumes L1, that's where we put our data, so we're fine. So we'll press enter again. Now the SX you see right here is your sample standard deviation, so that's your 9.3, which will give us the same value as if we'd done it by hand. Now on this test, I will ask you to do this by hand. And again, for the reason why some instructors expect you to know how to do it by hand. Now there's another problem that I may ask you to find a standard deviation on, and population or sample, and I won't specify by hand. Realize only if I say do it by hand do you need to pay attention to that, because the other one may have 30 problems, may not come out, or 30 numbers may not come out nice at all. Okay, so the SX is our sample standard deviation. The one right below it, that's O with a flip, that's our sigma x. That's our population standard deviation. So whether you're given a problem that's asking for sample standard deviation or population standard deviation, one of our stats will give you both of those. And okay, and I put the steps here to refresh your memory. Now if you just want to find a sample standard deviation, here's the buttons on how to do it. I don't like this. One of our stats does everything. Every semester I keep thinking I need to just delete this slide. But if you are just curious and find the sample standard deviation alone, this is the buttons for doing it. Enter values into L1. Be sure to exit out, so do a second mode. Then we press second stat, choose math, choose standard deviation, enter second one to put L1 on there, closing parentheses, and then enter. Now our variance. The measure of variation equal to the square of the standard deviation. So I'd ask you for variance in a problem. Well, very simple. You'd square your standard deviation. So like here, when I get this value, I'd want to square it. So let me show you. Okay, so I've just done the square root of 1032 divided by 12. You can put a closing parentheses at the very end if you want. Don't have to have it. And we get this. We immediately press the x squared and press enter, and that would tell us our variance is 86. Now variance, in terms of the sample, as soon as I get my little pen to work here, there it goes, is represented by s squared. So that would be our sample variance. Now population variance is sigma squared, like that. So it's very simple. Now if I'm using technology, okay, so I go through and I do one var. I have entered my numbers in. I go and do one var stats. So I press stat, right arrow to calc, do enter on one var stats, enter again. And I'm asked to find sample variance. Well, let me get a piece of paper. If you're not very good with technology, yet you're still trying to use it, you'd want to jot down the if you got the newer versions of the T84, you have to jot down the number, I think. So I'm going to do S is 9.273618495. Okay. Now what we're going to do is we're going to type that in, then we're going to press our x squared. So do 9. Now you notice how on mine it cleared the display. That's why I say I think, because the newer T84s is what this software is revolving around, and that's why you have to kind of jot it down before you start this. And then push your x squared button, and then enter, and that would give us our sample variance. Okay, let's say you're into technology. You've done your stat, you've done your calc, one var stats, and you come up with SX. There's a vars button here. If you press this vars button, the fifth one down, our statistics, I'm going to down arrow to it and press enter on it. You can also press the number 5 directly, and it does a down arrow and enter for you. Now once I go into that, you see the third one is our SX. So if I choose 3, then I don't want to have to type the number in. It'll handle that for me. Then I push the x squared, and it'll give us that. Now notice there's no kind of rounding error on this either when you do it with this. Now these vars only work after you've done one var stats. They don't work if you've done just the single mathematical function, standard deviation or mean. Those ones I said I should delete out. So if you've done one var stats, you can do that directly. Okay, let's say it's asking for population standard deviation, population variance. Okay, I'll go through my steps on technology. I do my stat, I do my calc, I do my one var stats, press enter. Again, the sigma x here is your population standard deviation. So if I'm good in technology, if you're not good in technology, then jot that number down and then type it in and press your x squared. But if I'm good with technology, again, I'll push the vars, I'll choose statistics, press 5, I'll choose 4 for the sigma x, our population standard deviation, and then I'll push the x squared, and then enter. And that'll give us our population variance, if you had a problem asking for that. Now to review our symbols. These are the 6 very important ones. Throughout this class, you'll need to know what these represent, because you'll see them, and they won't always tell what they are. Let me grab a drink real quick. Our first one is S. This is sample standard deviation. S squared is sample variance. X bar, sample mean. Sigma is population standard deviation. Sigma squared is population variance. and mu is population mean. Now, in comparing two sets of data, the larger the standard deviation, the more dispersion the distribution has. So the one with the largest standard deviation is more spread out. Now, I left this this particular PowerPoint in. Doesn't really apply to the current textbook, but I felt there should be some kind of general rule. Round-off rule. Carry one more decimal place than is present in the original set of data. So over here, these didn't have any decimal places. So for my answer, I took it to one decimal place. I wish all books had some kind of convention for that. Some of them just kind of, sometimes it's 2, sometimes it's 4. And I know depending upon the industry, depending upon what kind of precision they want, it would vary. But it'd be nice in books to be given that. Now, we don't do a whole lot with this in this class, so just besides just finding it. But this formula, the coefficient of variation, CV, this allows us to compare variation in different populations. And this describes the standard deviation relative to the mean as given by the following formula. CV equals standard deviation divided by mean times 100%. And I put those real generic because you could have a population values, population standard deviation, and population mean, or you could have sample. You could have sample standard deviation, sample mean. Let's take a look at example on that. And actually, let me save that page, and I got room for one more. Okay, so standard deviation, and let me say it's population values. So population standard deviation is sigma. So sigma is 2, and mu is our population mean, which would be 10. And it says find the coefficient of variation. Okay, let's go back to our formula. Formula says standard deviation divided by mean times 100. So standard deviation divided by mean times 100. And this is going to give it to us in percent form. That's 0.2 times 100, which should give us 20%. I hate decimals. Let's see, 0.2 times 100. Let me verify that. Yeah, 20%. Also, I hate making an hour movie and having a mathematical error in it, so I want to make sure. Now, again, this book doesn't do a whole lot of analysis of what does this represent and so forth. Just basically finds it. Now, another formula we can use to describe the skewness. Remember, skewness is when your data is skewed left or right. When you look at your bar graph, oops, I guess it's time to save it now. So, yes, measures of dispersion. Page 01. There we go. Remember, if we look at our data, and here's our bar graph, all the data appears to be on the left side. This is skewed right. So to describe the skewness of a distribution, this generally lies between -3 and 3. The closer it is to -3, the more it is skewed left. The closer it is to +3, the more it is skewed right. 0 indicates symmetric. Symmetric is where you get to get more or less your bell shape when you connect these together, the midpoints of your bar graph. Okay, so let's look at a formula dealing with this. It says mean is 60. The median is equal to 40. And our standard deviation is equal to 10. Well, how can you get this fairly fast? Well, one var stats gives you all this information, remember? Gives you mean, gives you median, and standard deviation. So if you've given raw data and they ask you to find the same thing, Well, use one of our stats, get these, and then plug them into your formula. Okay, so our skewness is equal to 3 times your mean minus the median divided by standard deviation. Okay, so mean was 60 minus the median, which is 40, over standard deviation, which is 10. 60 minus 40 is 20, times 3 gives us 60, so we got 60 over 10, or 6. Closer it is to negative 3, the more it's skewed left. The closer it is to positive 3, the more it's skewed right. Well, this is a positive 6. It's way beyond plus 3, isn't it? So this is skewed right. And again, describe the skewness of the following. So, well, there's a very crude way to tell how spread out the data is. You can approximate the standard deviation by taking your high value minus your low value. That gives you your range, and then divide by 4. Well, it isn't a very good measure, but sometimes maybe that's all you have. Maybe you don't have your actual data. You're just given the high value and low value, and they ask you to approximate the standard deviation. So that'd be the formula you'd use. Now, this is a minimum usual values, mean minus 2 standard deviations, and the maximum usual values, mean plus 2 standard deviations. So, for example, I don't got a problem on this, but let me make one up. You know, if they give you the mean and the standard deviation, so let's give x bar is 10 and s is 2. Sample mean, sample standard deviation. And they ask you what are the usual values. Well, the usual values go from mean minus 2 standard deviations to mean plus 2 standard deviations. And we'll look at this formula a little bit more, but applied to any values. So if I put that in, I got 10 minus 2 times 2, and 10 plus 2 times 2. 2 times 2 is 4, so 10 minus 4 is 6. 2 times 2 is 4, 10 plus 4 is 14. So our usual values fall between 6 and 14. So if you had a data point that was like 17, that would be considered unusual, not normal. Most of them fall in this area. Excuse me. Now, some of the times in statistics, they just ask you, is this unusual? Well, what they're referring to is this formula right here, if they give you numbers. Now we got our empirical or bell-shaped distribution. Now this is a 68, 95, 99.7% rule. This says about 68% of all values fall within 1 standard deviation of the mean. About 95% of all values fall within 2 standard deviations. And about 99.7% of all values fall within 3 standard deviations. If I look at this, I see in my bell curve here, the middle 2, that's 68%. And they're symmetric, the bell shape is. So the left side here would be 34%, the right side would be 34%. Then, 95% fall within 2 standard deviations. Now, unfortunately, the book has a little bit of a typo here. They put M for the mean. They should have put mu, because see how they put sigma for the standard deviation, which means they're talking about population values. Well, I stole this out of our particular textbook, so probably would have come up with my own if I had noticed that very begin with. They probably meant to replace the M's with mu, but they didn't. Now you can have population values here, you can have sample values, doesn't matter. But anyway, here's M here are means exactly in the middle. Now here over here is mean plus sigma, that's mean plus 1 standard deviation. I go one more out, that's mean plus 2 standard deviations. And then mean plus 3, and so forth. And this shows all the percentage breakdowns that fall in each little bar over here. That's going to become important later on. Okay, the important part in statistics or in life is the 95%. That's what we go off of. I always tell students they never study to get 100% on a test. Nobody does. To study to get 100% on a test, you would have had to read the chapter 3 times maybe. Start studying for the test a week, 2 weeks in advance. Go see tutors, work every problem, not just what's assigned, but every problem you could ever run across. Maybe buy another stats book, so forth. Now this is to study to get 100% on a test, to ensure 100%. Maybe the night before you'd study 8 to 10 hours. We don't have that kind of time. That's ridiculous to spend that kind of time. Most people study maybe to get 95% on a test. 95% is pretty good. That's still an A, isn't it? And it's very reasonable in terms of time and expense and so forth. Maybe 95% means do the homework, study an hour the night before the test, and maybe get a 95%. This is kind of true in life. We don't shoot for 100% because it just costs too much. So we shoot for an A range, 95%. And 95% is kind of a magic number. Excuse me. Now, using the empirical rule to determine percentage. First thing you need is your mean and standard deviation, and you may have to use one var stats to get that if you're given raw data. Then you map the mean and standard deviations to a blank bell graph, and then you add up the appropriate percentages you are wanting to find in the problem. Well, let's look at a problem dealing with that. Okay, let me move some of this. I've got some junk in my way here. There we go. And this is problem 5. And let me make that a little bit bigger. There we go. Okay, given the mean equal 20 and standard deviation is 2, use the empirical rule to find the following. Use the empirical rule. So mean is 20, and let me, it doesn't specify what, sample or population, but let me say, just so I don't have to write a lot, we'll say it's sample. So mean is 20, S is equal to 2. It says use empirical rule, so let's go back to here. Exactly in the middle is our mean. So that'd be 20. Going one standard deviation on both sides, this would be x bar plus one standard deviation, that's S, not 5. That would be 20 plus, and then the sample standard deviation was 2, so that'd be 22. Now going out this way, this would be x bar minus S. So this would be 20 minus 2, or 18. Well, go another one out. This is x bar plus 2s. So we've got 20 plus 2 times 2, which gives us 24. And this one would be x bar, this is what we're talking about mapping them, minus 2s. This would be 20 minus 2 times 2, or 16. Now once you see a pattern on these are very easy. See how it goes from 20 to 22 to 24. So this next one, which is our x bar plus 3s, I don't even have to plug numbers in, I know it's going to be 26. And this one out here, that's x bar minus 3s, 18, 20, 16, 14. Okay, now this one here has 34% in it. This one has 34% in it, just looking at these. Next one is 13.5%. This will be 13.5%. It's symmetric. 2.35. 2.35. And 0.15. Okay, so let's go back to our problem. A. Determine the percentage that falls between 18 and 24, inclusive. Between 18 and 24. And I'm going to use red for this. Here's 18 and 24. So 18 and 24. would be from here to here. So I'm going to add up all the percentages in there. So I got 34% plus 34% plus 13.5%. And so I don't make a math error, let me plug this in. Let's see, 34 plus 34 plus 13.5. That gives me 81.5%. So it says determine a percentage that falls between that. Well, 81.5% falls between those. Now B, determine a percentage that is greater than or equal to 22. I'll make this blue. Greater than or equal to 22. Well, here's 22. Greater than or equal to. That'd be everything to the right. So these three here. So I'm going to add together the 13.5% plus 2.35% plus the 0.15%. And we do that here. 3.5 plus 0.15. Of course, there's still a margin of error assumed with this that I'll type it in wrong into the calculator. That gives us 16%. Then C, I'll make it green, I guess. Determine a percentage that is less than or equal to 16 or greater than or equal to 24. So less than or equal to 16, here's 16. Less than or equal to would be that right there. Or greater than or equal to 24. Here's 24, so that'll be everything to the right. Okay, so here we got 0.15% plus 2.35%, and on this right side we'll have 2.35% and 0.15%. Oops. Now these add up to 4.7, and that's 0.3, so that gives us 5%. And that's how you work on the empirical rule problem. Now again, sometimes they don't give you the X bar and S. You have to do one var stats first to get those. So let me save this. And we'll continue on. I didn't want to play Tetris battle right now. Go away. Okay, let's go back to here. Now this is a note on if it asks you to find the actual percentage in a range with raw data. For example, let me work one over here. Given 3, 7, 15, 23, 35, 36, 37, 52, 81, and 103. Now the empirical rule isn't based upon the actual data. It's based upon an anticipation. Since it follows a bell-shaped curve, then we can predict this many fall in this range. But if the problem was actually asking you to find the actual percentage, find the actual percentage between 20 and 40. That's what this these steps are indicating right here. First thing, count how many are in the range. Let's say this is X. Between 20 and 40 would be this one, this one, this one, and this one. So there's 4 of them. So X would be 4. Second step, count how many there are total. Let's say this is in. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 of them total. Okay. Step 3, actual percentage is X divided by N times 100. So we got our X divided by N times 100. So we got 4 divided by 10 times 100. I think it's 40%, but let me double check. 4 divided by 10 times 100. 40%. So that's the actual percentage of them that falls between 20 and 40. Now we got Chebyshev's theorem. The empirical rule if it's bell-shaped. And Chebyshev theorem says the proportion of any set of data lying within k standard deviations of the mean is always at least this. Now the neat part about Chebyshev's theorem is it does not have to be a bell-shaped distribution. You'll find that this will hold true whether talking about skewed left, skewed right, or even the bell-shaped. Let me do an example of this. Say we want to find it within 2 standard deviations. Well, Chebyshev's theorem, we got 1 minus 1 over k squared. We've got 1 minus 1 over 2 squared, 1 minus 1/4, which gives us 3/4, or 0.75, which is 75%. So that says the proportion of any set of data lying within k standard deviations, the mean is always the least. So within 2 standard deviations, the proportion is always at least 75%. And I give those or that example plus another one here. If you plug in the 2, you get 75%. If you plug in the 3, you get 89%. Now, if you ever have a problem that asks you to find a range of values given the mean and standard deviation within so many standard deviations. So, for example, they give us x bar is 10, and sample standard deviation is 2, and they want to know within 2 standard deviations. Well, this is our k, so they're telling us k is 2. So our formula is x bar minus k times s comma x bar plus k times s. Now you may have to use one of our stats to get x bar and s, but x bar is 10 minus k, which is 2, times our standard deviation, sample standard deviation, which was 2, and x bar plus 2, oops, not x bar, better go back to bed, 10 plus 2 times 2, 2 times 2 is 4, 10 minus 4 is 6, and then 2 times 2 here is 4, which gives us 14. So within 2 standard deviations, this is our range of values. I did this problem, I think, earlier. I don't seem to be very random with my numbers I make up. But anyway, there's the official formula where k can be any value. I think the one I did earlier, I hard-coded 2. And that's the end of that section, so let me save this. There we go. Stop the recorders. So gotta find the recorder. And then stop the other recorder.